Hi, I'm Norman Wildberger. Today we're going to start this new course in hyperbolic geometry. And we're going to avoid the usual historical treatment, putting that off for a later discussion, and start off where I think the subject has its origins, with the work of the ancient Greeks, in particular Apollonius of Perga, who, after Euclid and Archimedes, was the greatest mathematician of the ancient Greek world, and the foremost geometer of that time. He lived in Perga in Italy from 260 to 190 BC, which was a few generations after Archimedes, and he probably saw himself as a rival to Archimedes. He's most famous for a treatise called Conics, of which 7 of the 8 books that he wrote survive. The last 4 come to us via an Arabic translation. In it, he proves many beautiful facts about conics. There are over 400 propositions in these books, and some of them are very important for us for setting up hyperbolic geometry. So let's talk a little bit about the ancient Greeks' point of view towards conics. By the time Apollonius came around, conics had already been studied. They'd been around for at least 150 years. And the way the ancient Greeks thought about them was as sections of a cone. That's why they're called conics. So a cone is obtained by taking a point and a circle, the point in 3-dimensional space lying outside the plane of the circle. And then we join the point with all the points on the circle with lines generating a cone. Now, before Apollonius came around, what people said was, let's take a cone like that, and let's take a plane which is perpendicular to one of the lines in the cone. Then that plane will slice the cone in a conic section, in this case an ellipse. And if we change the cone by making it either wider or narrower, then this ellipse can become a parabola or a hyperbola. By the way, this cone here that we're looking at is sometimes called a right circular cone. Circular because it has this circular cross-section, and right because the line joining the outside point to the center of the circle is at right angles, or perpendicular to the plane of that circle. It's also possible to consider so-called oblique cones, where the point down here is moved so it's not directly under or above the center of the circle. So Apollonius had a slightly more general point of view on conics. He said, well, what we can do is we can consider a cone just like before, but we don't have to consider a plane being perpendicular to one of the lines. We can choose any plane that we want intersecting this cone, and the nature of the conic that we get depends on the relative positions of the cone and this plane. So if a plane's coming in like this, for example, then we might get an ellipse. If the plane happens to be parallel to one of the lines of the cone, then we get a parabola. It only meets it in a one-sided curve that opens up and keeps going. And if the plane is, say, like this, then it cuts the cone in 2 branches of a hyperbola. And Apollonius realized that one wants to think of the cone as a 2-sided cone, not just everything above that point as earlier mathematicians had done, but actually thinking of it as lines also extending in this direction. So the hyperbola really has 2 branches, and Apollonius really liked those 2 branches of the hyperbola. So those are the objects that Apollonius studied, and he didn't work with the 3-dimensional picture too much. This was the definition of the conics, and then he took any one conic and quickly made it planar and studied it using planar techniques. So there are a few things that Apollonius discovered that are crucially important for us. Let's have a look now at the simplest conic, which is a circle. Circles were considered to be the most perfect objects in Greek geometry, and they were the center of study for a long time. So even Thales, the originator of Greek geometry, proved an important fact about circles, which is now called Thales' theorem, which is that if you have a diameter of a circle, namely a line that passes through the center, then for any other point on the circle, say C, this line here from A to C is perpendicular to this line here from B to C. So we say that a diameter always subtends a right angle at any point on the circle. That's Thales' theorem. Euclid, of course, was also very interested in circles and proved things about them. Here's one of his most famous theorems, that if you take a circle and you take two chords of a circle, a chord being just a line that meets the circle in two places, then we have four segments formed by those two intersecting chords, and there's a relation between the product of this segment with this segment and the product of this segment with this segment. Now, the ancient Greeks did not measure segments with a ruler. These days we would say that the length of this times the length of this is equal to the length of this times the length of this. Or better yet, in rational trigonometry, we would say that this quadrant times this quadrant is equal to this quadrant times this quadrant. But the ancient Greeks did not measure using a number system. They preferred to work directly with the geometrical lengths. So when they said this length times this length, what they meant was we create a rectangle whose two sides are the two segments in question. So I've translated the segment AE down here, translated the segment EB over here, and we've obtained a rectangle. Similarly, if we translate CE and translate DE, then we can form a second rectangle. And the content of Euclid's theorem is that these two rectangles are equal, by which he means that their areas are the same. So that has the same meaning as our arithmetical statement. It's a geometrical form for it. Archimedes, the greatest mathematician of antiquity, also studied the circle, and in fact wrote a little book called the Book of Lemmas that explore various interesting and novel properties of the circle that he discovered. For example, if you take a circle and you take a diameter through the center O, and then you build on this diameter two half circles. So you choose some point on it and choose one half circle there and another half circle there. Then the part of this upper half circle which is obtained by removing these two half circles, that green shaded area there, is called an arbellos, sometimes a shoemaker's knife. And Archimedes proved that the area of that arbellos was the same as the area of the circle who has diameter from this point to the point directly above it, perpendicular to the diameter. That red circle's area is the same as the green arbellos area. So the ancients had lots of interesting theorems about circle, but it was up to Apollonius to discover the most important fact about a circle. What Apollonius realized is that if you have a given circle, then automatically you have a remarkable connection between points in the plane and lines in the plane. The circle gives you a duality between points and lines. And here's how it works. So here's our circle in blue, our basic reference circle. We're assuming that circle is given to us. It's fixed in the plane, it's not moving. Okay, now choose a point. Call it A, and suppose that it's outside the circle. Then what we can do is we can look for the tangents from that point to the circle. These are lines that pass through the point and touch the circle just once. Just skim right by it, just touch it once. And there are two such tangents, one there and one there. And they intersect the circle at two new points, which we might call beta and gamma. And those 2 points, beta and gamma, determine a line. This line, capital A, depends on this point, little a. If we move the point little a closer to the circle, then this line moves closer also. If we move this one further away, then the line moves closer to being a diameter of the circle. And we introduce a bit of terminology here. We say that the point A is the pole of the line big A. And we say that big A, this line, is the polar of little a. So it's easy to get these terms mixed up. Remember that the polar is a little bit longer. It refers to the longer object, the line. Pole is shorter. That's the smaller object, the point. And along with this terminology, we're going to introduce some notation. We're going to say that capital A, or big A, is A perp, with a little symbol here like this, which is usually related to perpendicularity. So little a is big A perp, and conversely, big A is little a perp. So the relation is a two-sided relation. Given the line capital A, we can find little a, and given little a, we can find capital A. That's the polar, that's the pole. So it turns out that particular relation has a lot of very important properties that will be crucial for us for hyperbolic geometry. So let's get a feel for the relation between this pole and polar. We'll choose a fixed diameter of our circle going through the center O. There's our circle. And let's imagine what happens when the point little a moves along this diameter. So here's a starting position of A1 right there, and the corresponding polar line is capital A1 right there. As A moves out here to A2, the polar moves to this line here. We keep moving out, A3, now the polar is right here. As we keep moving further and further out, the polar starts moving towards this diameter. When we get exactly to the diameter, then the two tangents are parallel. And strictly speaking, there's no point that corresponds to those two lines because they don't actually meet. Or if you like, they kind of meet out at infinity in some nebulous sense. If we move the line just a little bit further, so it's on this side, then suddenly the two tangents meet somewhere on this side of the circle. And then as we keep moving this line towards this direction, the point A starts coming towards us. Here it would be right there, and for the line here it would be right there. So if we move the polar continuously like this, the point A goes off in this direction, seems to go to infinity, and then comes back on this direction also from infinity until it eventually gets to there. So we have a kind of continuity as A varies continuously on a diameter line. Big A, or A perp, varies continuously, always perpendicular to it. So all these polar lines are perpendicular to the diameter that we originally chose. A natural question now is, well, what happens if the point A is actually inside the circle? Is there some meaning to the polar of a point inside the circle? The definition that we've chosen suggests no, because it's not possible to draw tangents to a circle from a point inside it. But nevertheless, there is another definition of this polar-polar duality that's more flexible than the one I've given. So here is an alternate definition, in fact a better definition, of polarity. We sometimes say that this is a projective definition, because it turns out that it only relies on a straight edge. The only thing we need to construct the polar of a point is a straight edge. So here's our circle, which is fixed as usual, and here's our point little a. We want to calculate big A the polar of A. Okay, here is our previous construction involving these tangents, which are now secondary, so I've made them dotted. So we used to draw tangents, and then we joined those tangents. So that's the line that we're trying to get. Here's a new way of getting that same line. It involves 4 points on the circle. We're going to denote points on the circle usually by Greek letters. So Greek letters warn us that we're talking about points on the circle. So we're going to find alpha, beta, gamma, and delta, so that what? Well, so that first of all, the line joining alpha and beta, which we're going to just write alpha, beta, so that represents that line there. That line needs to go through the point A. And also, the line through gamma, delta, which is this line right here, it also goes through the point A. Basically what we're saying is we take the point A, we look at all the lines through it, and we choose 2 of them that meet the circle in 2 points. Okay? So no matter where the point A is, outside, in fact inside as well, we can always draw lines that pass through A that meet the circle. In fact, there's a lot of them that meet the circle. Any one of these lines passing through A would meet the circle, and we've just chosen 2 of them rather arbitrarily. So this is our notation for lines and the meet of 2 lines. So alpha, beta, that represents the line through alpha, beta. Gamma, delta represents the line through gamma and delta. And when we write one line followed by another line right beside each other, we're talking about the intersection or the meet of those 2 lines. So these 2 lines, alpha, beta, and gamma, delta, meet at A. That's this condition here. Now what are we going to do with these 4 points? We're going to form 2 other meets associated to them. We're going to take these 4 points and we're going to join them up in different ways. We're going to also look at the lines through alpha and delta, through beta and gamma, through alpha and gamma, and through beta and delta. So basically those 4 points determine altogether 6 lines. We've already got 2 of them, and now we're going to consider the other 4. They're in green. There's one right there, there's another there, there's another there, and there's another there. And those other 4 lines meet in 2 additional places. So point B will be the meet of alpha, delta, and beta, gamma. And the point C is the meet of alpha, gamma, with beta, delta. That's our notation. B is equal to alpha, delta, times beta, gamma. It means the meet of those 2 lines. C is alpha, gamma, times beta, delta. It means the meet of those 2 lines. And then we're going to join B and C, and that's going to be our polar line A. There's B, there's C. We're going to join them up, and lo and behold, we get the same line A that we got with our tangent construction. But this second construction, even though it was a little bit more complicated, it does not involve the rather tricky business of finding a tangent to a circle. In fact, this actually gives an efficient way of finding tangents to a circle, because we can do this construction first, and then these 2 points are determined by the line that we've just found. So now we come to a major theorem. A theorem is an important and crucial fact. And this is our first theorem. We're going to call it the polar independence theorem. And it is that the polar A perp does not depend on the choice of lines through A. What does it mean? Well, in this case, let's put our point A down here. The construction that I gave you in the previous slide for a polar require you first of all to start by choosing 2 lines through A. And then we did something that depended on those 2 lines that we chose. Now this theorem asserts that the polar that we end up getting does not depend on which particular 2 lines we started the construction with. So we're going to illustrate that in this diagram here. So here's the point A, and here is an initial choice of two lines. There's alpha, beta, and there's gamma, delta. So alpha, beta, and gamma and delta. 4 points determining two lines that pass through A and touch the circle in 4 points. Okay, and here's another example of our construction. What we did is we joined alpha and gamma and beta and delta to find the point C. And we joined gamma, beta, and alpha, delta to form the point D. And then we joined D and C and said that was the polar. All right, now suppose that we had chosen a different pair of lines. Instead of choosing these two lines as our starting lines, suppose we chose this one and this one. So then the 4 points would have been this gamma, this delta, and this one here, say nu, and this one eta. And then the diagonal points that we would have created would have been this one E here, and this one F here, and we would have found the polar by joining E and F. And lo and behold, you can see that in this particular case, at least, what we get by using these 4 points is the same as what we get by using these 4 points. We're always getting that particular line if we start with that particular point. And the theorem says that, well, this works not just for these 3 lines, but it doesn't matter which 2 lines you've used, you're always going to get that particular line. It's a very lovely fact. It's one of the most profound facts about a circle. Now this is a very rich diagram. I want you to stare at it quite a long time. Okay? You can spend a few hours thinking about this diagram. There's actually a lot in it. In particular, I want you to think about this first exercise. So this is exercise 1.1 because it's in our first lecture and it's our first exercise. So the exercises that I give you during the lecture, I wouldn't mind if you sort of stopped the video and said, all right, let's see if we can figure this out here before you go further. That will help you a little bit in understanding, putting together a mental picture of what's going on. So this particular exercise, in the diagram, describe C perp, F perp, D perp, and E perp. So for example, for C perp, well, here's the point C. You might say, well, how are we going to find the polar of that? We need to make a new construction. But it turns out that we've got enough lines in the diagram already without making any additional constructions to see where C perp is. Okay? And the same goes for F perp and D perp and E perp. So find those polar lines on the diagram already. So what about a proof of that theorem? Am I just going to state theorems in this course and move on and then not prove them? No, I'm not. Every time I state a theorem, I have an obligation to you to explain why that theorem is true. And in the back of your mind, you should say, aha, that theorem has not yet been proven. Wildberger still needs to give us a proof of that. He needs to convince us that that's true. We're not just going to believe him because he says so. Well, actually, you should believe me just because I say so, but you should also want a theorem to have a proof. Now, I'm going to give you proofs of the theorems that I claim, but I'm going to not necessarily give you those proofs right after I state the theorem. So sometimes it's good to have a theorem sit for a little while and to start understanding what it means before we tackle the often knottier problem of figuring out how it's proven. So now let's have a look at some of the advantages of this projective definition of polarity. So the first one we've already mentioned, it only requires a straight edge. We don't need actually to have a compass construction other than our initial circle, but once our initial circle is given, we only need straight edges to compute the polar of a point. And the second major advantage is that the construction works also if the point A is inside the circle. And let's give an example of that so you can see that in action too. So here's our circle. Here's a point inside the circle, point A, and we're going to use the construction to find the polar of that point. So what do? We choose two lines that pass through A that also pass through the circle. In this case, because A is inside, any line that goes through A will meet the circle in 2 points. So we can choose any two lines. So we'll choose this line and call these 2 points alpha and beta, and we'll choose this line, call the 2 points gamma and delta. And then the construction says, all right, you take those 4 points and you construct the other 4 lines joining pairs of points of those 4. So we construct this line alpha delta, this line beta gamma, this line alpha gamma, and this line beta delta. And where those 4 points meet gives us 2 new intersection points. Here and here. And we can call those points C and D. And then we join those points, and that join is the polar of A. So big A is the polar of little a, or we write big A equals A perp. Now when you look at this for a little while, you see that there's a kind of a symmetry here. There's a threefold symmetry between the points A, C, and D. So for example, although the polar of A is, yes, the line CD, it's also true that the polar of C is the line joining A and D. And the polar of D is the line joining A and C. And why is that true? Well, let's say this last one. Why is the polar of this one this? Well, it's because from the point of view of D, this is exactly the same kind of diagram that we had for the construction for the polar of D. Namely, you can think of these 2 lines as being the lines chosen from D to meet the circle in these 4 points. And then the other diagonal points will be A and C. So this will be the polar of D. So the same diagram actually has 3 different polar pairs implicit in it. So this is a course in mathematics. It means that I want you to actually learn the material. And to make that a little bit easier for you, I'm going to give you these exercises to practice on, to augment this sort of abstract information that I'm giving you with practical, hands-on experience. It's important to get that practical hands-on experience to complement and to strengthen the abstract knowledge that's coming into. So our second exercise is to construct polars of various interior and exterior points A and verify the polar independence theorem. Verify it in the sense of checking that it actually is working in special cases. So I want you to choose lots of points, inside, outside, and use the construction to find the polars of those points. Start getting a feel for, if you've chosen a point A, can you predict sort of offhand where the polar is going to be? Now, the picture that we drew last time has another interpretation, another way of sort of thinking about it. Maybe a more symmetrical way of thinking about it is by saying, well, why don't we just start with 4 points on the circle? So we'll start with 4 points alpha, beta, gamma, delta on the circle. And our notation for points on the circle will be null points. We'll call points on the circle null points. So if we start with alpha, beta, gamma, and delta, then we have a quadrangle. Okay, in projective geometry, 4 points are called a quadrangle. 4 lines are called a quadrilateral. So if we look at this quadrangle of 4 points, then it has a diagonal triangle. So now we're thinking of just looking at all 6 lines that are created by these 4 points. And those 6 lines are now all sort of symmetrically equal or on the same footing. And they meet in these 3 points, which are called the diagonal points of the quadrangle. And the triangle formed by them, DEF, here's my notation for a triangle, just means 3 points, which are not collinear. This diagonal triangle has 3 polar pairs. As we've seen, the pole of the point D is this line, the pole of the point F is this line, and the pole of the point E is this line. So each of the sides of this diagonal triangle is the polar of the opposite vertex. And to make that polar correspondence a little bit more obvious, I've used colors so that this red point is related to this red line, and this green point related to the green line, and this blue point related to the blue line. When I can, I will try to generally do that so that you can see polar pairs a little bit more easily. So that's a rather nice symmetrical situation. So please make some versions of that for yourself too. See how it all goes. Great, so we've understood this polar construction, and now we get to the main fact about this duality. We'll call this the polar duality theorem. Here's the theorem, is that if A and B are any 2 points, then A lies on B perp precisely when B lies on A perp. So precisely when is what I prefer to use instead of if and only if, but it means the same thing. So I'm saying that if A lies on B perp, then B lies on A perp, and if B lies on A perp, then A lies on B perp. So both of these statements imply the other. Here's a diagram that illustrates the situation. We have a point little a and its polar A perp. We have a point B and its polar B perp. In this case, we see that A happens to lie on B perp. And the theorem tells us that if we know that A lies on B perp, then automatically B has to lie on A perp. And conversely, if B lies on A perp, then A has to lie on B perp. So we're going to assume that we already know the polar independence theorem. So here's a proof. And this diagram here illustrates what happens. So let's suppose that A lies on B perp. We're going to try to prove that B lies on A perp. Okay, so A lies on B perp. First thing that we do is we choose null points alpha and beta so that A lies on alpha beta. In other words, we choose one line through A, in this case this one, that meets the circle in 2 places. No matter where the point A is, whether it's inside or outside, we can always choose a line through it that meets the circle in 2 points. And we'll choose that line and call these 2 points alpha and beta. Alright, now what we're going to do is we're going to find null points gamma and delta so that B lies on alpha delta and beta gamma. What does that mean? Well, basically it means we're going to join B to alpha and see where that line meets the circle a second time. We're going to use the fact that every line that meets a circle once meets it in a second place. With, I should say, the stipulation that if that line happens to be a tangent, then that second point is the same as the original point. That's a sort of limiting case when the 2 points coalesce. So here, this line here, through B and alpha also meets the circle in a point delta. And this line through B and beta also meets the circle in the point gamma. So we started with A, we chose this line arbitrarily, got these 2 intersections alpha, beta, and now we're just choosing the other intersections that we get by looking at things from B and calling them gamma and delta. But alpha beta times gamma delta lies on B perp. So let's have a look at these 4 points now. Okay. These 4 points can be used to construct B perp, because these 2 lines go through B. So I remind you that the construction involves connecting alpha and beta and gamma and delta, and that's 1 point. Whatever that point is, that's a point on B perp. And then we could also join these 2 points and these 2 points to get the other point, but we're not going to need that one. The fact is that alpha beta times gamma delta, the intersection of those 2 lines, lies on B perp. But A, the point A, also lies on alpha beta because we started it that way, and it also lies on B perp. So the point A also has the property that it lies on this line and by assumption on this line. So the point A must actually be the meet between alpha beta and gamma delta. In other words, A lies on gamma delta. We've proven that this point A must lie on gamma delta. But then B lies on A perp. Because now if we consider these 4 points in relation to the point A is lying on these 2 lines, so we can look at the polar construction for A perp. And one of those points that we need to get is by joining these 2 points of our quadrangle. So B has to be one of the points that we use in the construction to find A perp. So B must lie on A perp. So we've shown that if A lies on B perp, then B lies on A perp. And the situation is completely symmetrical, so the other direction is the same. If B lies on A perp, then A lies on B perp. Okay, I want you to understand this proof. I want you to go through it, make sure you understand the argument. Tell your friend, try to convince your friend why this is true. It's a very important fact. All right, a bit of notation. Let's call our distinguished circle the null circle, and denote it by a script C. We're going to be using a fixed circle a lot in this course, and that circle is always going to be the same circle. We'll call it the null circle. It will always be denoted by C. Okay, now we have a second important theorem, pole of a line theorem. That every line, big A, which is not a diameter of our circle, is the polar of a unique point, little a, called the pole of big A. And here's a proof. Take any 2 points, B and C, lying on big A. Then construct the polar of B and construct the polar of C, and define A to be the meet of those 2 lines. So the pole of big A will be obtained by taking the meet of the polars of any 2 points lying on big A. All right, so exercise 1.3, fill in the details of this proof. This is sort of the idea of the proof. I want you to wrestle with it, make sure you understand it, write down the details, and illustrate it with some careful diagrams. Exercise 1.4, what happens if our big A line is actually a diameter? Why did we have to exclude the case when big A is a diameter? All right, so that finishes our first lecture. We've introduced the important idea of polarity, going back to Apollonius, and pinpointed some key facts about this polar duality. This is at the heart of hyperbolic geometry, this notion. So it's really important that you understand this first lecture. In fact, generally the first steps in a mathematical journey are typically the most important ones. Next time we're going to stick with Apollonius, and we're going to talk about something else that he discovered, intimately connected with this polar business. It's the idea of harmonic conjugates, or a harmonic range. So that's what we'll do next time. I hope you'll join me for that. I'm Norman Wildberger. Thanks for listening.